We will discuss a special case of epipolar geometry under the same topic of stereogeometry, and that is affine epipolar geometry. So, we discussed earlier also how an affine camera differs from a general projective camera. In an affine camera, your center of projections or camera center that lies at infinity, which means that the projection rays, they are all parallel to certain directions, and the basic projections, basic imaging mechanism, it takes place through that parallel projection. So, let us consider a stereo system which is formed by two affine cameras. You can see here in this diagram that there are two such cameras, and there are directions. So, it is a parallel projection ray which is forming images in the second camera. Similarly, in this is the direction ray for the first camera, and the camera centers, this is lying at infinity, this parallel projection. So, the intersection of these projection rays will be at infinity, which will define the camera center. Effectively, that is the direction of these rays itself. So, now how the epipolar lines are formed? Epipolar lines are actually, they are all parallel lines. Here we can see that for the same projection ray, if I take the projection of the scene points lying in this projection ray, then all those image points, they will form an epipolar line. And since all the rays are parallel here, all the rays are parallel in the first camera, epipolar lines also should be parallel. And the form of fundamental matrix, particularly when you have this kind of geometry, it gets simplified. You can see the structure here. You have only 5 non-zero elements. See, all the 4 elements in this part, they are 0, and the other elements are non-zero, and so there are only 5 parameters. But since once again the scale is involved in this representation, so there are 4 independent parameters. So, here this is a summary. So, projection rays are parallel, and epipolar lines and planes are also parallel. That is the characteristics of an affine epipolar geometry. And the other thing is that as epipolar lines are parallel, epipoles are in the form of E1 E2 0 transpose. We know that because the intersection of epipolar lines, that would be also at the point at infinity, which means the value at the third dimension representing scale should be 0. So, let us again elaborate this particular property. Consider this affine stereo. X is corresponding to x prime, y is corresponding to y prime, and there exists a homography between them when all these points are lying on a particular plane pi. So, that is the plane induced homography. And so, epipole or point of intersection is represented as E1 prime, E2 prime 0. We have seen that this is the structure, and following the same construct, the epipolar line is given by E prime cross H A x, because this is the homography transformation of y to y prime, which will lie also on the epipolar line, and epipole also lie on the epipolar line. So, E prime cross H A x equals 0. So, F A should be E prime cross H A, and since epipoles have this construct, so all those 4 cross 4 submatrix of the affine fundamental matrix in the upper side, that becomes 0 because of this structure. So, you can see that E prime cross itself is having this structure, and if I multiply with H A, it would look like this. So, particularly you notice that the right epipoles these are given by this particular column. So, the values of the right epipoles, it has occurred in this fashion. So, E2 prime comes here and E1 prime comes here. So, similarly, we will see also the values of the left epipoles will be at the row. So, left epipole will be also, as I mentioned, similarly DE minus DE 0, and right epipole is given by minus E1 prime by E2 prime 0. So, from the structure of affine fundamental matrix, epipoles are very easily determined, that we can see. Right epipole is minus B A 0 if this is B, this is this is E2 prime, E1 prime. So, this should be ZB and this should be A. Yeah, it should be minus. So, this should have been also minus. Minus of this value is E1 prime. Right. So, this is B, this is A. We consider this value is B and this value is A. So, we will have, I mean this value rather is B and this value is A. So, we will have minus B A 0. So, this is the representation, right. And similarly, right epipole is minus D E 0, this is the representation. So, these are the two things. For estimating this affine fundamental matrix, we have to use the corresponding epipolar lines. So, L prime is given by this f x, a b x. So, this is the derivations we can see, and finally, given two pairs of points, you get an equation in this form, a x prime plus b y prime plus e x plus d y plus equals 0. So, once again, because of the structure of the fundamental matrix is simple, only there are 5 unknowns. So, this equation becomes in a much more simpler form, and you can represent the set of linear equations again in the matrix form in this way, and you can solve using direct linear transform. Since there are 4 independent parameters, you require only 4 point correspondences to get f a, and from the structure itself singularity is satisfied, because of the structure that all the upper submatrix 2 cross 2 submatrix are, all of them are 0. So, if you take the determinant, you can check that the determinant value itself is 0 in this general structure. So, you do not have to perform any special operations to enforce singularity. So, that approach was using the set of correspondence points, where you can form linear equations exploiting these constraints of epipolar geometry, and we have seen how you can solve those problems, solve those equations, which becomes simpler for the case of affine fundamental matrix estimation. Now, we can use another approach for estimating the fundamental matrix. Here, we can compute the homography induced by a plane by using 3 point correspondences. So, minimally we require 4 point correspondences. So, we have seen already that if we would this affine homography, this homography would be also affine homography, and for that 3 point correspondence is sufficient to compute it. So, we can do that, and then we need to compute the epipolar line. Now, in this case it is sufficient to compute the epipolar line L prime, because from there itself we can get the epipoles. The directions itself, direction of epipolar line itself will give you the epipoles, because that is what its direction cosine is given in this form L2 minus L1, and that is what is the 0. So, actually epipoles is a point at infinity at the along that directions, and this is direction of the line. So, in this way epipoles can be obtained. So, now you can have H A and you have E prime. So, E prime cross H A, that would give you the corresponding affine fundamental matrix. So, we have come to the end of this particular topic of stereogeometry. So, let me summarize its different features that we discussed. First, we discussed epipolar geometry in a stereo imaging system, and there we have seen that epipoles, scene point, corresponding image points and camera centers, all of them lie on the same plane. Then fundamental matrix characterizes a stereo system, and it is unique to that stereo setup. It has various properties like transformation invariance is one of the properties. That means transformation of image points will give me back the fundamental matrix. You can use the transform points to estimate it. Then it is a 3×3 singular matrix with degree of freedom 7, that is the number of independent parameters is 7, and since it is singular, its determinant has to be 0, rank has to be less than 3, and in this case for a fundamental matrix its rank will be 2. So, and its function is that it transforms an image point into its epipolar line in the second camera plane, second image plane. So, and this the relationship is that you have to multiply the fundamental matrix with the image point in the homogeneous coordinate representation, then you will get a line in the homogeneous coordinate representation in the image plane. And for any pair of corresponding points, you get these relationships x prime transpose f x, that should be equal to 0. If we get epipoles E prime, then this is the relation f e and E prime transpose f, that should be equal to 0. So, they are the zeros of fundamental matrix, epipoles are the zeros of the fundamental matrix. E is the epipole in the reference camera plane. So, it is the right 0 of f, and E prime is the epipole in the second camera plane, and it is the left 0 of the fundamental matrix. On the other hand, if I change the convention of reference camera that swap them, then F transpose will be the fundamental matrix, and all these results are consistent with that representation. So, given camera matrices P and P prime in F is unique, that we discussed, and particularly these computations we should note that if we have the projection matrices in this form, that projection matrix in a canonical form of I 0 and P prime as capital M M, this is the representation, then fundamental matrix is given as M cross M. So, we discussed the definitions of these notations in our lecture. Please note the corresponding representation. Or you consider a very generic representation. I have given you the expression. So, this I did not really expand or discuss in my lectures, but please go through it, note this expression. So, what you will find that from P and P prime we have computed the epipole, and which is given by this M prime here, which is given by this expression M prime minus M prime M inverse M. So, this is how the epipole is given. That means, you have to take the image of the center of the first camera. So, image of the center of the first camera is given in this form, and then the homography at infinity is given M prime M inverse. So, that is how we get this fundamental matrix. Then we discussed that how projection matrices are related with fundamental matrix, though a pair of projection matrix give uniquely one fundamental matrix, but a fundamental matrix can lead to a family of pairs of projection matrices. Because if you have a homography in the 3-dimensional space, like which means it is a 4×4 non-singular matrix, homography of a 3D projective space, and then P prime, if it gives F, then PH P prime H will also give the same fundamental matrix. Then given a fundamental matrix F, there exists a family of stereo setups or pairs of camera matrices that we need to note. And this is one example of a family of matrices, considering the reference camera is given always in the canonical form of I0, then you can express this family given that fundamental matrix by its epipole and any arbitrary 3 vector and a arbitrary scalar constant, as you can see in that expression which has been shown here in this case. Then given a camera matrices P, P prime and a corresponding pair of image points x, x prime, it is possible to reconstruct the respective 3D sim point x. We have discussed 3 approaches for this, and one of them was using the triangulation geometry. The second one was using geometric reprojection error using nonlinear optimization technique, and third one is the algebraic form of representation of triangulation approach, and that is how we can derive the structure. Then let us summarize also the facts regarding essential matrix, which is a fundamental matrix of calibrated camera, and this is given in this structure. That is, if I consider a stereo system where projection matrices are given in this form, that reference camera is a canonical matrix I0, and the second camera is related by the rotation of axis and translation of origin. So, in that case essential matrix is given by those parameters only, and one of the properties of essential matrix is that 2 of its singular values are equal and the third one is 0. Then you can compute these components T prime cross and R by matrix decomposition of E such that E equals SR, where S is a skew symmetric matrix and R is orthogonal. And if you have this decomposition, then you can compute also its projection matrices, which are shown here, that apply singular value decomposition of essential matrix, and there could be 2 possible decomposition of this essential matrix, which is shown here in this form, that use the singular value decomposition matrix U and V, and there are 2 special matrix Z and W, which is shown here in this form. Then the expression of S and R is given as you can see, and from there you can compute P prime. So, note here this U3 is the third column of the matrix U of the singular value decomposition, which means this is the column vector corresponding to singular value 0. And one of the above is valid in viewing a point from both the cameras. And then we discussed also estimation of fundamental matrix. So, given a set of pairs of corresponding points, it is possible to estimate fundamental matrix. Minimum 7 pairs of points required. We have discussed one particular method where we have seen that how the eigenvectors corresponding to 0 eigenvalues, they are used in this case, 0 eigenvalues, so eigenvectors of a system. Then parametric representation of a fundamental matrix is given in this form. This is particularly this form also contains the epipoles. You should note that there is a little bit of ambiguity in representing E prime and E. E prime should be E here and E should be E prime here. So, that correction you should note, we discussed there also, and this should be E prime. And given a set of pairs of corresponding points, it is possible to estimate camera matrices and scene points up to projective ambiguity, which is 4 cross 4 homography matrix. So, this is a particular fact that if I use the 4 cross 4 homography matrix and multiply transforms P as PH, similarly P prime as P prime H, then any scene point can be also transformed as H inverse X and H inverse, this should be X prime, H inverse X. So, that would give me the same corresponding pairs of points. So, you will get the same fundamental matrices. Then given a pair of corresponding lines L and N prime and camera matrices P and P prime, it is possible to reconstruct respective 3D line L. We discussed that also. So, in this case you can compute the plane formed by the lines L and also camera center. We know that is P transpose L, and also the plane formed by L prime and camera center of P prime, which is P prime transpose L prime, and then two planes they intersect at a line which is that corresponding 3-dimensional line. So, that also you can reconstruct. So, this is what intersection of planes P transpose L and P prime transpose L prime. Then we discussed about plane induced homography. So, a plane induces homography between corresponding image points in a stereo setup. So, this was the expression for the homography for a particular description of the camera matrices and the plane. So, plane described by say V transpose 1, V transpose and 1, V transpose gives the directions of normal of the plane, and camera matrices are given by I 0, that is the canonical camera matrix of the reference camera, and capital E, that is a general camera matrix. Then the homography induced by that plane is given into this form. This is the outer product of A and V transpose, A and V. A special case of this homography, the plane is at infinity, that induces H equals A. You note that in that case your V transpose becomes 0 column vector. So, this part, this component is equals 0. So, you get simply A. We also discussed about affine epipolar geometry, which simplifies the structure of fundamental matrix. Like this is the structure what we discussed. It has only 5 non-zero, maximum 5 non-zero elements, A, B, C and E, D, C, and this is the structure. So, the epipoles they are given by it is the right epipole, which means the left epipole is at minus B A 0 and the right epipole is minus D E 0. And there also we are having the same confusion. Left epipole is the epipole of the, we are having the same confusion here. It is F A minus B A 0, that would be 0, which is the left epipole. So, it should be right epipole, and similarly minus D E 0 and F A, that should be equal to 0, which is actually the right. So, please note this correction once again here also. So, this is left epipole. Left epipole is the epipole at the left image plane and right epipole is the epipole at the right image plane. I think with this we have come to the end of this particular topic, and we will be discussing our next topic on feature detection in the next lecture. Thank you very much.